Now the next very important thing that we have, it's a very cool thing, a very amazing result that will help you solve a lot of area problems. This is the main thing for today's session, the star of today's, the lotus ratio lemma. Now these configurations that I've been telling you, you may find projection theorem at places. You won't find the extended projection lemma or the X configuration or the lotus ratio lemma. This was a privately done work of one of the very brilliant teachers in India, Alok. So this is not my work, Alok Kumar. So I've been privileged enough to study from him Euclidean geometry. So yeah, he trains the IMO team of United States and India as well at the IMOTC, and he has been observer of the Indian team as well multiple times. So yeah, he framed these. He named it lotus ratio. I don't know if it's out there on the internet. I'm not aware of that, but we'll be doing this. This is a very helpful thing, and you'll realize when we do the problems. It will solve a lot of problems. So we have this sort of setup. I want you to remember the configuration. We have BP by PE. BP by PE we need to find. It equals BF by FA into 1 plus AE by EC. Now it looks like a very complicated thing, isn't it? Now to memorize this, look at it like this. So you go from BF, then FA, then AE, then EC, and you end. For BP and P. So if you have to start from BP by PE, you go from here. You start with BF, then FA, then comes AE, then EC. BF, FA, 1 plus AE, EC. You have to just add 1 plus. Similarly, for CF, PF, CP and PF, you have to do CE, EA, AF, and FP. Yeah, CE, EA, AF, and FP. This direction. All right. Now, let's look at the proof of this. How do we prove this? Let me just bring down the diagram a bit. Yeah, okay, the F got down. It's okay. We have proof. Okay, so we have to prove, let's say, one of the results, BP by PE. It's all an exercise of similarity. It's all. So BP by PE equals BF by FA into 1 plus AE by EC. This is what I need to prove. So I need to find similar things, similar triangles. What I'll do is, I'll do a bit of construction here. I'll make a line parallel to this. Alright, I'll call this X. Sweet. Now I have a lot of things. What do I have? I have in triangle ABE, Fx. By construction, I have drawn Fx to be parallel to BE. I'm constructing, let me just write it here. Construction, draw Fx parallel to BE. Sweet. Now what do we have? In triangle ABE, Fx is parallel to BE. Now can I say that AF by FB equals to AX by XE? AF by FB equals to AX by XE. This is the result that comes out of similarity. We do triangle AFX similar to triangle ABE. Triangle AFX is similar to triangle ABE. How are they similar? Since this angle is common one, since these two lines are parallel, this angle is equals to this corresponding angles, and this is also equal to this. Again corresponding angles. So by triple A, they are similar, and then we have these ratios. So I can say that, right? All right. So I'm starting to get some of the things here. Now can I find one more pair of like similar triangles, like the same sort of result? Now I want you to look at triangle CXF. Why? Since Fx is parallel to BE by construction, Fx is also parallel to all parts of BE, that is parallel to PE as well. PE, Fx. Now focus on this triangle. Once again, we can find a similar ratio. Can I say CE by EX equals CP by PF? Yes, we are accidentally we are proving the second one, not BP by PE, but for CP by PF, this ratio. So we have two equations. You can eliminate this and like solve these two, and you'll end up with the second one, this one. And if you draw a parallel line like this, once again you'll get two such equations and you'll get the first one. So this is a really important result. Now coming to problems, how are we going to use these? I hope you remember the first lemma that we did in episode 2. We'll be using that. So this is in continuation. This was the second most important thing. This was lemma 2. Apart from projection, the extended projection, the X configuration, we have the lotus ratio lemma. I want you to pause a bit and review a bit and then proceed. All right? Everything that we have done till now. So we have the problem here. We're provided with a triangle, D and E are points. Okay. So we have BD equals DE equals EC. BD, DE, EC. F is the midpoint. So this is also equal. Okay. Okay, they are intersecting here. Determine the ratio of the area of APQ to PDEQ. Notice that they always ask for ratios. If they ask you to find areas specifically, they give one of the areas. Unless they've given an area, you have to deal with ratios. So in the first session, in the second episode, the first session of lengths and ratios, I told you we'll be shuffling between ratios of areas and ratio of lengths, right? We have ratios of lengths from BD equals DE equals EC. Can I say the ratio is 1 is to 1 is to 1, since they're what? They're equal. So I'll call this 1 to 1 to 1. Sweet. Same goes for these as well, since F is the midpoint. Now, you have to spot that hidden configuration once again, the lotus ratio configuration. This, remember this. So this is what you have to spot. There are a lot of, like two of them. So I want you to look at this. In triangle ACB, the bigger one, this triangle, the bigger one, focus on these two. Forget about this AD thing, forget about this. Focus on these two. Okay, why are we interested in that? What's the intuition behind? We have to find, look at what we have to find. APQ by PDEQ. APQ by PDEQ. Right? How do we do this? Remember the lemma one. What was it? In the previous session we did that. If this is a random line, this is DE. This ratio is P, this is Q, this is R, and this is S. Then area of ADE by area of ABC, the bigger triangle, is going to be PQ into P plus R into Q plus S. We have discussed the proof and all. P plus R into Q plus S. We have to find this by this. Isn't this the same configuration? Now, we have to find something of this sort here. Yes. What do we need? We need ratios. Of what? These sides. How are we going to find the ratio? This is what this ratio we need. P, Q, R, and S. How will we find these? Using the lotus ratio. So that was the intuition behind looking for the lotus ratio. See, Q and S. That is what we do. Let me draw a path diagram. Alright, so here we are. This is the bigger triangle. And there you go. Yes? No, sorry. So we have this. Yeah. So we have ABC and FE we are interested in. This ratio is 1. This is 1. This is 1, but this is 2. It gets divided here, so it's 1 plus 1. 1 plus 1. So this whole thing, we are ignoring the BD thing, alright? AD thing, sorry. So we have this 2 is to 1, 1 is to 1. We are interested in this ratio, PQ. So P by Q is going to be what? We'll start from this side, we'll move here. It's going to be AF by FC into 1 plus CE by EB. AF by FC, CE by EB. Yes? What is AF? That is 1 by 1. AFFC, that's 1. So 1 into 1 plus. What is CE? CE is 1. 1 by 2. So that is going to be 3 by 2. P by Q. We have it. It's actually Q by S. Here I have written Q by S. So we need to do that. So we have Q by S to be 3 by 2. Sweet. We have one part of the triangle. Q and S. That's 3. This is 2. Ratio, not the length. Alright. Now one more part diagram. We'll look for this P and R. This is ABC, right? Now we'll be ignoring the AE part. We'll be focusing on AD. And this will remain as it is. So this is going to be AD, right? This is 1, this is 1. This time this is going to be 2 and this is 1. We are interested in what? In this ratio. Or this one, right? So P and S, P and R. Okay. So we're interested in this one. So we'll begin from here and once again go there. So it's going to be 1. So let me write it like so that you don't get confused. So B by R equals AF by FC into 1 plus CD by DB. You need to memorize this. Alright, so AF by FC is 1. 1 plus CD by DB is 2 plus 1. 2 by 1. So it's 3. So P by R is 3. Or we can say 3 is to 1. So this is 3, this is 1. Now, what is it? This is P and Q. Right. So P and Q. So do we have area of APQ by area of ABC? Can we write this by the first lemma? Yes. We'll say P into Q, that is 3 into 3, that is 9, by P plus R is 4, into Q plus S is 5, that's 9 by 20. Yes. Now we didn't have to find this. We had to find APQ by the quadrilateral, that is PQCB, if I'm not wrong. It's actually DE. Okay. Here we have marked it wrongly, so it's DE. So PQDE. What we'll do is, this is 9 already, so it's the ratio we're dealing with. So the total is 20. So the left out part, since the total is 20, this is the part that's left. This is 9. So this is going to be what? 11. The answer is 911. 9 by 11. Okay. That's a great answer. People watching from United States. Alright. Now, how helpful is this lemma? I want to show you the official solution of this problem. This appeared in CRMO 2012. Look at this. What they're doing is they're doing that common base and common height thing that we did in the first episode, in the second episode, first session of lengths and areas. So they're doing that. They're doing constructions and stuff, and it's so complicated. This is a very inelegant solution. You can also use the Cheva's theorem that we'll be doing later. It actually like comes from the same area thing that we did, and you can use coordinate geometry. Yes, that would make it easy. It's inelegant, but this one is the easiest one that we did. You can pause the video and read the solution if you can understand that. Alright, so this is a really easy way. So the lotus ratio lemma, how useful is it? I hope you've got. So I hope you remember this and value this. This result is really important.